algorithm complexity. We use the notation T sub an to represent the computational cost for solving a problem instance of size n by algorithm A, shorted as Tn. However, different instances of the same size may lead to very different computational costs. So here we discuss three types of Tn. The first one, worst case running time. It is very often discussed. Tn equals the maximum running time of an algorithm on any input of size n. So that's the worst case. Sometimes we are also interested in average case running time, and that is the expected running time of an algorithm over all inputs of size n. In order to calculate the average case running time, we need to make assumptions on input distribution and use probabilistic analysis technique. And third case, best case running time. Here Tn equals the minimum running time of an algorithm on any input of size n. Okay. So here we have defined what is the complexity of an algorithm and what are the three cases. Next, now we have to answer the question how to measure the running time, because we know algorithms are implemented by different person using different language, compiled by different compilers, and executed on different platforms. So how can we get rid of this difference in terms of architecture, operating systems, compilers, programming languages, and so on? So we need to compare on an ideal platform or a model. And this measurement needs to be human, language, and machine independent. It basically just describes the nature of the algorithm directly and precisely. In order to do so, we measure the running time on this RAM model, random access machine model. In this model, each instruction takes a constant amount of time. For example, in this model, read-write memory cell, arithmetic operations, comparison operations, go-to operation, and so on, they all take a constant amount of time and no concurrent operations. We use the RAM model to measure the running time as the number of basic operations. This RAM model is a simplification and abstraction of computing platform. So if we use number of basic operations to measure the running time of your algorithm, this measurement is machine independent, and we can compare the efficiency of algorithm directly and precisely. Furthermore, we are more interested in big enough problems. So we want to answer the question, when the problem size is big enough, how does computational cost grow? And we're going to look at the growth of Tn as n is growing larger or bigger. And this is called asymptotic analysis. This asymptotic analysis can be used to compare the complexity of two algorithms. Like for example, when n gets large enough, a theta n square algorithm always beats a n cube algorithm. Now, let's summarize some of the concepts we have discussed so far. For algorithm complexity, we have discussed three cases. We have discussed how to use red model and asymptotic analysis to measure the running time. And we also talked about we need to use some asymptotic bounds to compare two algorithms. And these asymptotic bounds are big omega, theta, and big O. You're probably very familiar with the notation of big O. So here we are going to learn the two more asymptotic bounds, big omega and theta.